In this video, we solve problem 10.1.13-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says, listed below are numbers of internet users per 100 people and numbers of scientific award winners per 10 million people for different countries. We're asked to construct a scatter plot, find the value of the linear correlation coefficient R, and find the p-value of R. Then we're asked to determine whether there is sufficient evidence to support a claim of a linear correlation between the two variables. And we're asked to use a significance level of alpha equals 0.01. So I have this data set. It's actually pretty small. I've got 1, 2, 3, 4, 5, 6 ordered pairs here. And we're asked to construct a scatter plot from this data. So what I would do is I would use Excel to construct that scatter plot. So I would click on this, then I would say open in Excel. And when I do that, I have this list right here. So I would just highlight all of that data and then go to Insert. And then I have a little image that looks like a scatter plot. I'll select Scatter and I see my graph. Now they're making the x-axis a little bit longer than the y-axis, but let me make sure that my first variable is first. I've got an internet users per 100 of 79.3 and award winners at 5 or per 10 million at 5.3. So the 79.3 is on this axis and then the 5.3 is on this axis, the y-axis. So yes, this is plotted correctly. So I'm looking for a graph that looks like this in MyLab Statistics. So if I'm choosing among these, I'd say that this one looks the most like my scatter plot. Now, if you're doing this problem or a problem that's similar to this on an exam and you don't have access to Excel, what I would recommend is just plotting one of these points. Plot 79.3 and 5.3. And then look for the graph that has that point on it. So I'd go over here, I'd say, this is obviously not it because there's no 79.3 and then 5.3 on it. And then D is obviously not it. So it would have to be this one or this one. And then I would zoom in on each of these graphs and use process of elimination from here. So I know it could be this one or it could be this one. So that one has the 79.3 and the 5.3. Then look over here, this one. Does this one have the 79.3 and the 5.3? It appears to have that point as well. So then I would say, okay, well, what are the major differences between these two graphs? Well, this one has a very low number of internet users and a very high number of award winners over here. So if I look at this a little bit closer, this point, if it looks like, what are these tick marks? Is that 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90. So each of those tick marks represents an increase of 5. So it looks like we've got some number of internet users. That number is a little bit less than 40. And then I've got a number that's very close to 12 here. Then I would look at this list. And when the number of internet users is a little bit less than 40, the award winners is not 12. The award winners is 0.10. So that looks much more like this. So that's how I would use process of elimination to infer this graph if I didn't have access to Excel. I would just plot a point and then narrow it down. And then after that, look for some points that might be able to tell you the difference. Whether or not that particular graph that you're looking at is actually consistent with the data that you have. So I'll check my answer and they like my answer, great. And then they ask for the linear correlation coefficient R, and they're asking us to round to 3 decimal places as needed. Now we know that there are a number of ways that you can calculate R. The easiest way, if you have access to technology, is to just use the technology. I use Excel and I use that function Pearson in Excel. We will use that here, but I also want to show you how to find R using one of our formulas. So I will share my paper with you so that we can do that. And it makes sense to use this as an example for that because our data set is so small. Okay, so if I'm using my paper, if I'm using pencil and paper to do this, I need to use this formula. I know that this is a lot of arithmetic, but for such a small data set, when we have 6 ordered pairs, it made sense to practice using this formula for this set of 6 ordered pairs, excuse me. So what we're going to need here is a column for the x's squared. We're also going to need a column for the y's squared. We're going to need a column for x times y for each of these numbers. And then we're going to have to sum up all of those columns. And n, that's our sample size. N is equal to 6. That's the number of ordered pairs that we have. So we're going to use this formula, and then we're also going to use the function in Excel that allows us to find the linear correlation coefficient R. And we're going to show that we get the same thing either way. Okay, so in order to use this formula, we need an x squared column, we need a y squared column, and we need an x times y column. So for the x squared column, I'm just taking each of my x values and I'm squaring them. And that's really it. Now you're going to type all of these into your calculator and actually find out what those numbers squared are. And that's why we typically use technology for something like this. Even when we're using the formula, we might use Excel for this. So it's just a little tedious. Got 62.88 or 6288.49 here, then 81 squared. And you got the idea. We're just going to square each of those numbers. And those are my x's squared. And then for the y's squared, we're going to do the same thing. I'm taking each of my y values, and then I'm squaring them. I think I'll pause my video and then just square these, and then I'll show you the result. So after we actually square them, these are the numbers that I got. So you could do that on your own and check if you want to. See, make sure that you're entering this into your calculator correctly. And then we also need an x times y column. So I'm just taking this x value and I'm multiplying it by that y value. So I've got 79.3 times 5.3. And I have 81 times 8.7. 57.1 times 3.2. Okay, so we've got all of those columns. Now in our formula for the correlation coefficient R, we need the sum of all of these. So I need the sum of the x's in my formula. I need the sum of the y's. I need the sum of the x's squared. And I need the sum of the y's squared. And I need the sum of x times y. So we're just going to add all of these up in every column. This is where Excel is really handy. Sometimes we type things into our calculators incorrectly, especially if we're rushing through our homework or something like that. So I'm just adding all the numbers in each column. You get the idea. And I will do that for these other 3 columns as well. So I'm going to pause my video and then I'll do that while the video is paused. Okay, so after I added up all the values in this column and this column and this column, these were the results I obtained. I will need all 5 of these quantities when I use the formula to compute the linear correlation coefficient R. Now, before I do that, I want to check these values. I want to make sure I didn't make a mistake either when I was writing this down, writing the numbers down in the first place. Sometimes you just make a transcription error. Sometimes you write down a 3 when you mean to write down a 2, or you invert a couple of numbers when you're writing something down. I always like to check my answers against some other source. So I think I'm going to use Excel to do these calculations as well. So let's go to Excel and do just that. So I will select I'll type equals, and then I'll select the X value, and then I'll use that caret and raise it to the second power, hit return or enter, and then just drag and drop. I'm going to do the same thing with the Y values. I want the Y's squared, so I hit equals, then I choose the Y value, then I square it, doing caret 2 there. Then I hit return or enter on your computer, and then you want to drag and drop. And then we want the X's times the Y's, so we'll hit equals X times, and then select the cell for the corresponding Y value, and then you want to drag and drop. And then for each of these, I want the sum of the values in that column. So I'll take the sum of the values here, and then I want to drag and drop to the right so that I get the sum of the values in all 5 of these columns. Okay, so the sum of the X's is supposed to be 401.8, and that's what I have on my paper. That's good. The sum of the Y's is 29.7, great. The sum of the X's squared is 28,266.46, good. The sum of the Y squared is 231.41, good. And the sum of the X's times Y's is 2,264.39. Excellent. Okay, so my hand calculations are the same as the calculations that Excel would do for me. So that tells me that I'm on the right track. Now I'm just going to substitute all of those values into this formula. Remember, our sample size was 6. That was the number of ordered pairs that we had. So n is equal to 6. In the numerator, we have 6 times the sum of the X's times Y's. And that is 2,264.39. And then we're subtracting the sum of the X's, which is 401.8. Oops. Times the sum of the Y's, which is that 29.7. Oops, there we go. And then in the denominator, we see a couple of expressions that look like this. Our sample size is 6 for both of those. And you want to be really careful here. This is the sum of the X's squared. It's not the sum of the X's and then squared. You have to take the X's, square them, and then add them together. So this value comes from this column. And I did not leave myself enough space. I'll put 2 dots, 3 dots there. That's the 28,266.46. We want to subtract the sum of the X's squared, which is that 401.8, and we're squaring that. Over here, I'm taking 6 and I'm multiplying it by the sum of the Y's squared, which is at 231.41. And then we're subtracting the sum of the Y's, and then we square that result, and the sum of the Y's was 29.2, or 29.7. Okay, so there's a lot of room to make arithmetic errors here. You just have to be very careful about your order of operations. I would probably do the numerator first. Let's do it. Oops. So we have 6 times 2264.39 minus 401.8 times 29.7. And that gives me a 1652 88.88. And then what I would recommend is each of those square roots. I would do those, well, actually, let's do the expressions under the square roots first. So I have 6 times 28,266.46 Then we're subtracting 401.8 squared. And we've got 8155.52. That's under a radical. And then we want to do something similar over here. So if 6 times 231.41 minus 29.7 squared. And this is 506.37. And there's a fact from algebra. The square root of a times the square root of b is actually just the square root of a times b. So the simplest way for me to evaluate this in my calculator is this way. I'll take that 1,652.88 and I'll divide by the square root of this 8155.52 times 506.37. And that's going to give me my R value. If you're saying, gosh, this is tedious, you're absolutely right. But this is actually how they did all of the statistics before technology was available. They came up with a formula that was meaningful. And then they said, how can I write it in a form that makes it really easy if I have my X's and my Y's? Like, how can I make hand calculations just easy to apply? And then they came up with this formula. All it involves is squaring some X's and squaring some Y's and multiplying some X's and Y's together and then making a lot of substitutions. So even though it's a little tedious, it's not too bad. And we see that our R value is approximately 0.813 if we round to 3 decimal places. So that was the answer that was requested of us. That's how we would do it by hand using this formula. Now let's use Excel to see if we can get the same result. I want to use Excel using to do the computation for this formula and see if I get the same answer. And I also want to use Excel's built-in Pearson function, which will allow me to find R as well and compare and make sure that we're getting the same R value either way. Okay, so I want to use Excel to evaluate that formula. So I'll just do the numerator and denominator separately. The numerator was our sample size 6 times the sum of the X's times Y's minus the sum of the X's times the sum of the Y's. Great. In the denominator, we have the square root of sample size of 6 times the sum of the X's squared minus the sum of the X's squared. That's in our first square root. I want to put all of that in parentheses. And I want to multiply that by, open parentheses, for the second square root of 6 times the sum of the Y's squared minus the sum of the Y's squared. Close parentheses for the square root, close parentheses for that entire square root multiplying the first square root. Hit return, and numerator over denominator should be the value of R. So now I'm just using Excel as a fancy calculator. And I get that 0.813358. That's great. And then using Excel's built-in function, let's calculate R this way. We type equals Pearson, open parentheses, and it's asking you for an array for that group of X values and an array for the group of Y values. An array is just another name for a vector, or just a list of numbers. Or actually, I think it's another name for a matrix. So I select the first one and then I hit a comma. So I select, let me do that again. So for the first array, I'm selecting the X values. I drag and drop that corner, and I want all the X values. Make sure you don't include the sum. And then in the second array, I want all the Y values. Notice that Excel has highlighted it in a different color. That's exactly what you want. And then hit return and see we get exactly the same value for R. So most of the time I'm going to use Pearson's R function in Excel to compute my R value. But I wanted to show you at least once how to use that formula to calculate it by hand. And with this being a data set that was so small with only 6 values, it seemed like a good opportunity for us to practice that. And we see that we get the same answer either way. Now, this calculation would be much easier if we had small integers, which is more likely if you were to see a problem like this on a quiz or an exam in our class. Okay, so we want to type the linear correlation coefficient as 0.813. Excuse me, rounding to 3 decimal places is needed. Great. And then we're asked to determine the null and alternative hypotheses. Now remember that rho is the linear correlation coefficient for the population. R is a linear correlation coefficient for our sample. So the null hypothesis is always whenever we're looking for evidence of a correlation. The null hypothesis is always that there is no correlation, so that that linear correlation coefficient is equal to 0. Or at least in this class, it is always that the population linear correlation coefficient is equal to 0. And then if we are saying, is there a correlation or is there not a correlation? The null is that there's no correlation. The alternative hypothesis is that there is a correlation. So that means that the linear correlation coefficient in that case would be non-zero. And then we're asked to compute the test statistic. I will share my paper with you for this one as well. So the test statistic T is a t-score from a student t-distribution corresponding to the sample statistic R. Now, the R value is a sample statistic because it's computed using our data. Now we want to know, well, how extreme is that R value? Given that R is distributed with a distribution that can be approximated by a student t-distribution. So we're going to use this formula in order to calculate R, or in order to calculate the t value corresponding to R with n minus 2 degrees of freedom. So n was equal to 6 in our case. So n minus 2 degrees of freedom is going to be 4 degrees of freedom. And the R value was approximately 0.813. And we're taking that and we're dividing by the square root of 1 minus that 0.813 squared divided by that sample size minus 2. So that's the number of ordered pairs minus 2. In this case, that's 4. So we would get something that looks like this. So that's my actual R value. I think I want to use that R value rather than using this rounded version. So I'll take that and I will, how can I store this? Maybe it's that button. And then we go to alpha. And I want to store it for a variable, let's say x. Oops, that's an old x value. I think I just zeroed out my tested or my sample statistic R. Oh well, I guess I'm just going to have to use this rounded one. I forgot how to do the storing the value of the variable in this calculator. It's been a long time. So we'll just do this instead. That's okay, it's not going to be as accurate. But I have 0.813 and then I'm dividing by the square root of 1 minus 0.813 squared. And then we're going to take that whole thing and we'll divide by 4. Notice it's all under the radical. And I get a t-score of approximately 2.793. Or if I round to 2 decimal places, which is what they asked me to do, I get 2.79. Now, if I want to get the exact value of t using this formula, I can use Excel, and hopefully I get about 2.79 when I round to 2 decimal places. So let's use Excel for that. That way I don't have any error due to that rounding at least not for those, those first few decimal places. So for my test statistic t, I would hit equals, and then the r value. Then we're dividing by the square root of, open parentheses again, 1 minus the r value squared, divided by the sample size, which was 6 minus 2. And I get 2.796. So when I use the exact r value, if I was rounding to 2 decimal places, I would get 2.80. But if I use the approximate r value of 0.813, I get 2.79. So it's just 0.80 or 2.80 or 2.79. Those are pretty close. I think Excel would or MyLab Statistics would probably accept both of them. So I will use the 2.79 from the approximation. Let's see if it likes that. Okay, it's good enough for them. And then it asks for the corresponding p-value, and they want us to round our p-value to 3 decimal places as needed. Now that requires going back to what we learned about p-values that correspond to test statistics t when we talked about hypothesis tests in chapters 8 and 9. So I'm going to share my paper with you so that we can talk through that, and then we will use Excel to do the calculation of that area in the tails that corresponds to the p-value. In order to find the p-value, we need to look at the alternative hypothesis and see whether we're looking at a left-tailed test, a right-tailed test, or a two-tailed test. Well, whenever we are dealing with correlation, so if the question is, is there a correlation or is there not a correlation? In all of those cases, the alternative hypothesis is that there is no correlation. That means we're dealing with a two-tailed test. And since we're dealing with a two-tailed test, this probability that corresponds to our R value of R equals approximately 0.813. This is the probability that R is 0.813 or more than that, or negative 0.813 or less than that. That probability is equal to the probability that our test statistic T is greater than this 2.79 or equal to that. Or on the other side, it's equal to negative 2.79 or less than that. So this should be symmetric. I didn't do a very good job at making it symmetric, but the p-value is that this area under this probability density function for the student t distribution, and that area is just this area, but it's twice that area because of the symmetry, because we don't care if we're far off to the right or far off to the left. We're just interested in that area in both tails whenever we're looking at a two-tailed test. So the p-value is twice the probability that our test statistic is greater than or equal to 2.79. So we could use t.dist.RT for right tail and multiply it by 2. Then we'll have a 2.79 here, and then we've got 4 degrees of freedom. That's one way of doing it. Or we could use a two-tailed test. We could do t.dist.2t in Excel. That's going to make it a two-tailed test, and we'll have 2.79 and 4 degrees of freedom as well. The two-tailed test gives you the area in the nearest tail and then doubles it. And that's exactly what we're doing here. We're finding the area in the nearest tail and then we're doubling it. So we should get the same answer either way. So let's find out what that area is using Excel now. So my functions are, I want p equals 2 times t.dist.RT for right tail. And then we want this test statistic t, and we want 4 degrees of freedom. So we have 0.049 as the p-value there. Or we could use the two-tailed test. So we could type equals t.dist.2t, open parentheses, And we want this test statistic and 4 degrees of freedom. So in either case, we get the same value, which is what we should get, and that's a p-value of 0.049 when we round to 3 decimal places. Let's enter that in MyLab statistics and see if they like this value. So I have 0.049 here. Okay, great. And then we want to compare that p-value to our alpha value. Remember, p-values are probabilities. They're associated with area under the curve for a probability density function. So we're saying that the R value that we obtained, the probability of getting an R value that we obtained, or an R value that is more extreme than that, is approximately 0.049. So our probability of getting an R value like ours is about 4.9%. We have a 4.9% chance of getting an R value like ours, or an R value that's more extreme than that. Now we're going to compare that probability to this alpha of 0.01. So we've got a significance level of 0.01. Sorry, there's hair on my face. So we're comparing this 4.9% to this 1%. Since we've decided that 1% is our cutoff for what we consider to be significant, this 4.9% is not enough for us to consider this a significant value of our sample statistic R. Since our p-value is greater than our alpha value, and our alpha value is our significance level, then we're going to say that there is not sufficient evidence to support the claim of a linear correlation. Now notice that if our alpha had been 0.05, there would have been sufficient evidence to support the claim of a linear correlation. That was our choice. We chose alpha equals 0.01, or someone chose alpha equals 0.01. And given that choice, we do not have sufficient evidence to support the claim of a linear correlation. And that is it for that question. See you next time.